So welcome everyone to the E3SM webinar. And I'd like to introduce Siddhartha, or Sid Vishnu, who I've had the pleasure of working with for the past 3 years. He has an undergraduate degree from the Indian Institute of Technology, ITT, and then he came to the United States to Florida State University and has master's degrees in applied and computational math and another one in physical oceanography. And then he started a PhD in scientific computing, which is when I met him. And I thought his qualifications are so perfect, and we really hit it off. And so I've been lucky enough to be his advisor. And he just defended his thesis 2 weeks ago. And so this is what you get to hear about today. Welcome, Sid.
Thanks so much, Mark. It goes without saying that I've learned a lot being here at LANL with you and other scientists. And so today I'll be talking about the theme of my doctoral research, which is time-stepping methods for PDEs and ocean models. So I'll get started right away. Here is a broad outline of my talk. It can be broadly divided into 2 parts. On the spatial and temporal order of convergence of PDEs, the first one consisting of analytical derivation, symbolic algebra, and numerical experiments, and the second part focusing on time-stepping methods for ocean models, consisting of the barotropic baroclinic splitting and filtering of the barotropic modes, and the verification suite of shallow water test cases that I designed for the barotropic solver of ocean models. Now move on to the first part. Now, instead of starting with the motivation, I thought I might adopt an unconventional approach here. I'd like to virtually engage all of you with a mental exercise. Imagine that you are solving this hyperbolic PDE, ut equal to f, and you are already equipped with an exact analytical or manufactured solution. You have a spatial discretization of order alpha and the time-stepping method of order beta here, belonging to the method of lines. Now, before the machine precision error dominates, you have already reached the asymptotic regime where the truncation error is dominated by the powers of delta x and delta t rather than their coefficients. Then, for a stable numerical scheme, if the global solution error is of the same order of accuracy as the global truncation error, what would you expect the order of convergence to be in the asymptotic regime for refinement only in space, only in time, and for refinement in both space and time, keeping delta t proportional to delta x? Now, while you think about the solution, let me tell you that I have derived the full expression for the local truncation error of a generic hyperbolic PDE over 1 time step, and I've used analytical methods by hand, symbolic algebra packages, and verification by numerical experiments. Now, the global truncation error at a time horizon is 1 order of delta t less and is given by this expression here, which reduces to this highlighted one for delta t much less than 1. So if the global solution error is of the same order of accuracy as the global truncation error, what happens if you are refining only in space? The order delta t to the power beta term dominates and you cannot attain convergence. Similarly, if you're refining only in time, the order delta x to the power alpha term dominates, and again, convergence is not guaranteed. Now, only if you refine with delta t kept proportional to delta x, then you can attain convergence at the rate equal to the minimum of the spatial and temporal discretizations in the asymptotic regime. So what can we learn from this slide? What should our strategy be for developing an ocean model, or any model for that matter, that involves hyperbolic PDEs? Once we have finalized upon the spatial discretization scheme, which is of order alpha, we should be choosing a time-stepping method of order beta such that beta is greater than or equal to alpha to obtain the maximum possible order of accuracy in the asymptotic regime. But then again, we do not gain any further improvement in the order of convergence for beta greater than alpha. So within a specific family of time-stepping methods, our optimum choice is beta equal to alpha. Now, is the order of accuracy everything? Not quite, but it certainly plays a crucial role which we simply cannot ignore. Yes, in some applications like ocean modeling, stability and the convergence of some physical quantities are assigned high priority over accuracy, and the magnitude of the error is also important, right? Imagine that you are using a high order spatial discretization and a low order temporal one, and the coefficient of delta x to the power alpha term is it far exceeds than that of the delta t to the power beta term, and you do not reach the asymptotic regime before the mesh precision error takes over. So you observe that the error converges with the high order of the spatial discretization. Now, if that happens, I would argue that you got lucky, and such a situation may not always arise. So your safest bet would be to just add up the strategy that I just mentioned in the slide. Now, this table is nothing but an expanded version of this one, like this column. All it says is that if you refine to delta t kept proportional to delta x in the asymptotic regime, the order of convergence is the minimum of the spatial and temporal discretization. So the fourth column is the minimum of the first and the third ones. And I have numerical evidence for the rows highlighted in yellow in the first part of my talk and the ones highlighted in green in the second part. Now I'll move on to the motivation. Any typical graduate level textbook on numerical analysis typically contains standard predictor, corrector, and multi-step time stepping methods applied to ODEs in one chapter, followed by spatial discretization operators of PDEs in another. But in real world application, the discretization of a PDE and the order of convergence consists of both spatial and temporal convergence, especially if you're refining in space or time or in both. And this is what I investigate in my research, the simultaneous dependence of the local truncation error for varying orders of discretizations. Now, so my derivation consists of 3 parts by analytical means, symbolic algebra, and numerical experiments. So this is the theorem which is central to the analysis. Now, given the exact solution of a hyperbolic PDE at time level Tn, the exact solution at time level Tn plus 1, that is at Tn plus delta T, can be obtained by Taylor expansion about Un and Tn. It assumes this form. Now, the numerical solution at Tn plus 1 is obtained with a method of lines time integrator. It assumes this form, where the f hat k plus order delta x to the power alpha term is basically the numerical equivalent of the fk term, which is the temporal derivatives of order k, and the f hat k term, it satisfies this equation for a method of lines time integrator of order beta. As a result, the local truncation error at Tn plus 1, which is basically the difference between the exact and the numerical solutions, it assumes this form, where this C beta plus 1 term is not equal to 0. Now, there is a fundamental reason as to why you arrive at this form. If you mentally walk through the stages of any method of lines time integrator, you'll see that you need to evaluate this right-hand side f term, which is referred to as the tendency term in ocean modeling jargon, at fractions of a time step for a predictor corrector or a deferred correction method, or at previous time levels for a multi-step method. Now, for given values of the independent and dependent variables, the tendency term is always exact for an ODE. But for a PDE, the tendency term consists of spatial gradients like this one. And so it always carries with it an error of order delta x to the power alpha, alpha being the spatial discretization order. So this order delta x to the power alpha term cannot be disposed of in the final form of the local truncation error. Okay, but wait, I can still verify the order of accuracy by refining only delta x or delta t. Am I contradicting myself? Not quite. Imagine that you are refining only in time by a constant factor, keeping the spatial resolution fixed. What happens if instead of plotting the actual solution error norm, you plot the norm of the difference between the errors at every grid point, or the norm of the difference between the numerical solutions at every grid point? Because after all, the exact solution doesn't really care about the spatial resolution or the time step size. Well, in that case, this order delta x to the power alpha term here gets cancelled, and you can attain convergence with order equal to that of the time stepping method. And similarly, if you refine only in space, you can verify the order of accuracy of the spatial discretization. But please remember that this exercise is only meant to verify the proper implementation of the spatial and temporal discretizations. Convergence of the actual error norm cannot be attained with only spatial or temporal refinement in the asymptotic regime. And as a matter of fact, under certain circumstances, if you just keep delta x constant and refine time, refine only delta t, the error can actually get worse. The simplest example would be advancing the linear one-dimensional homogeneous constant coefficient advection equation discretized in space with the up to infinite difference scheme, and you are advancing it in time with the first order forward Euler method. These are the leading order terms of the truncation error, and you can see what happens if, while maintaining the Courant number C less than 1, if you just simply refine delta t, the term within the parentheses, the magnitude of that term increases. And because of this uxx term, the order is diffusive in nature, and this is exactly what you see in the plot here. Like on the right hand side, and I mean both of these plots are using the same delta x, but the right hand side one has a delta t which is 20 times less than the one on the left, and you can see the error is higher here. So now I'll move on to the derivation by symbolic algebra, and I developed this symbolic Python library containing a Taylor series expansion in X, Y, and Z, like in 1D, 2D, 3D, which is imperative for arriving at the local truncation error expressions. For the generic ODE, ut equal to A. For the generic hyperbolic PDE, ut equal to A of u and the spatial gradients and the independent variable space and time, and specific ODEs and PDEs of this form. And I used linear variable coefficient hyperbolic PDEs as well as nonlinear ones like the nonlinear Burgers equation. And also, if like pxqx assumes this form, then that is, and then you can see that the PDE, this hyperbolic PDE reduces to the ODE, and so does the truncation errors, so that our method is robust. Now I've used first, second, third order spatial discretizations for the PDEs, 5 explicit time stepping methods and 3 implicit ones belonging to both predicted character and multi-step ones. So this is just a snapshot of the 2 simplest cases where you're looking at the leading order truncation terms of generic hyperbolic PDE. This is the one for the specific PDE, UT, like this one, the linear variable coefficient one. And it's a war between like this term and this term, which determines the order of the local truncation error. And as I was saying before, if the PDE is reduced to the ODE, like and then you can see that this expression reduces to this one for the ODE. For instance, this term is equal to this one if P equal to P naught. If Q equal to Q naught plus Q1x, so this QX becomes Q naught. So this term reduces to this one, and this term reduces to this one, and so on. Now, finally, I have some numerical evidence. So I used finite difference methods and finite volume methods for spatial discretization. In the first row, you're looking at the finite difference one with it's the first order upwind one, and you are looking at refinement in both space and time, keeping delta x proportional to delta t, refinement only in space and refinement only in time. And this is the linear variable coefficient advection equation. And to avoid situations leading to better than expected order of accuracy due to coefficients of the leading order terms being 0, which is kind of common with test problems involving just a sine wave mode, I choose our exact solution to be a superposition of 2 wave modes with different amplitudes, wave numbers, and phase speeds, and specify the initial and boundary conditions accordingly. And as you can see, we have already reached the asymptotic regime with the finite difference method, and the order of convergence at delta t kept proportional to delta x is given by the minimum of the spatial and temporal discretization. So it's always first order, no matter how high order you go in time. It doesn't really matter at all. Now with the finite volume method, I use the piecewise parabolic reconstruction in space. In a couple of words, like starting out with the cell average solution, what the PPR, or the piecewise parabolic reconstruction, what it does is it interpolates the solution to the edges, but the fluxes are defined, and this interpolation is fourth order accurate on a uniform mesh. And then it applies the monotonized central slope limiter and adjusts the edge estimates to flatten any local extremum and ensure that the resulting scheme is oscillation free and monotone. Now, even though these monotone slope limiting strategies ensure stability, it unfortunately comes at the cost of accuracy. And as you can see, it for some of the schemes, some of the time stepping methods, it reduces the both spatial and temporal orders of accuracy. But you still see that you at least need an order of accuracy, you at least need a time stepping method of the same order of accuracy as the spatial discretization, which is about 3 here, to attain the maximum possible order of convergence. And for some methods, like let's say the Adams-Bashforth ones here, you can see that you can see the order reduction. It starts out with 3, but eventually the order of accuracy it reduces to like 2.62, and for the nonlinear equations with the same methods, it reduces 2.3. So yeah, this is the nonlinear inhomogeneous Burgers equation used with the manufactured solution, the same solution as a manufactured one. So now I'm going to transition to the second part of my research. So the truncation error analysis and the associated convergence studies, they apply to any hyperbolic PDE. But that was not the theme of my doctoral research when I started working at LANL. And I was being funded by DOE to improve the time stepping algorithm of LANL's MPUS Ocean. And last summer, I was conducting this convergence study with the coastal Kelvin wave test case using the barotropic solver of MPUS Ocean, and I was unable to attain higher than second order accuracy, no matter how high of a time stepping method I was using. So this is what motivated me to delve into the analysis. Now, sometimes in ocean modeling and other applications, we pick a good enough spatial resolution and test a time stepping method by refining only in time. But now we know that it does not guarantee convergence of the actual error norm. So now I'm going to switch to this second part of my talk and address some challenges associated with time stepping methods in ocean models. So the primary one is the disparate timescales problem. So basically, ocean models like permit motions ranging on a wide range of timescales. We have the surface gravity waves at 100 meters per second phase speed, and the internal gravity waves and the currents being like traveling at speed 2 orders of magnitude less. So this imposes a tremendous constraint on the time step because just the existence of the surface gravity waves forces it to be much smaller. But it's really impractical to advance the model with the smallest time step dictated by the fastest waves due to from the CFL criterion. So how do we deal with this? We resort to operator splitting, where we split the momentum equations into 2 parts: a barotropic part for solving the depth independent fast 2D barotropic waves, which are advanced in time either explicitly with a small time step or implicitly with a long time step, and the baroclinic part for solving the much slower 3D baroclinic waves. This is a schematic here of the splitting. And of course, before you reconcile the barotropic variables with the baroclinic counterparts to arrive at the total 3D states, we need to apply a time averaging filter about the barotropic solutions to minimize the mode splitting and aliasing errors. So these are some time averaging filters that I've incorporated in MPUS Ocean. What was the basic rectangular filter with full range was there before, and then I used rectangular filters of range half and 1/4 and 3/4, and this is a cosine filter, and this is a Hamming window filter. You're looking at the primary weights in red and the secondary weights in blue. The primary weights are what are used to time average the barotropic variables to center them at baroclinic time level n+1, and this is for the fluxes to be centered at baroclinic time level n+12, which are used for advancing the tracer equations. So the Hamming window filter is basically a raised cosine filter, and the last two ones are the filter designed by Alexander Shepetkin and Jim McWilliams, and they can be optimized for second order accuracy or minimal dispersion. And the special features is that they have negative weights, so that they just extend to 120 to 130% of the baroclinic time step, which reduces the number of barotropic computations considerably. Okay, so I performed a surface gravity wave simulation with Emperor's Ocean and also a nonlinear shallow water Python solver. And you're looking at the solution here with the various time averaging filters and the superimposed on the RK4 solution, because that's what we have for the because we don't have an exact solution at our disposal. And then these are the results with the nonlinear shallow water solver. And because we cannot perform the typical barotropic baroclinic splitting here, we freeze the slow nonlinear terms, which is equivalent to the barotropic average of the baroclinic terms. And we varied both the filters and the forward backward parameter gamma, which can also provide dissipation. So the main takeaway from this table is that you need the appropriate amount of dissipation, not too much of it, because it can damp out the entire solution more than necessary, not just the spurious oscillations. So the ideal combination is a narrow filter with a large parameter gamma, or a wide filter with a small parameter. Now, finally, I have the verification suite of barotropic test cases, and now the motivation being, like any numerical model, one is a suite of verification exercises for testing spatial and temporal discretizations. And these are the test cases that I've designed, consisting of dispersive and non-dispersive geophysical waves, barotropic tides, and some standard mathematical test cases like these ones. And I developed this unstructured mesh ocean model in Python, employing the tree-space spatial discretization and all these time stepping methods, like the standard ones and the ones more popular in ocean modeling, like the generalized forward backward ones. So due to the time constraint, I will be just showing you two of these test cases. And this is the coastal Kelvin wave test case. Now, instead of using a one sine wave mode, I to be able to distinguish between the dispersive versus non-dispersive nature of the waves, I used a superposition of two sine wave modes, one having twice the amplitude and half the wavelength as the other one, as you can see here. And because it's dispersive in nature, the coastal Kelvin wave, both the modes propagate with the same phase speed. Then I have the inertia gravity wave, which the restoring forces being inertia and gravity, but it's a dispersive wave, so the two wave modes propagate at like varying phase speeds, and you're looking at the section along the diagonal here. And these are the other waves. And yeah, so just to speak a little bit about the manufactured solution technique, it's a useful technique to test the implementation of the variable coefficient terms, the nonlinear terms, and the bottom topography in the prognostic equations. It may not be possible to design a test problem with an exact solution satisfying the original prognostic equations involving this term. So we simply manufacture our solution, and typically, so this one is just a sine wave. But our manufactured solution is a smooth one in space and time, and insert it in the prognostic equations and determine what the right-hand side is going to be, most certainly not 0. And then we numerically solve this slightly modified set of equations consisting of the source terms on the right-hand side. So this is just a table just showing that what various test cases test the implementation of the various terms, the bottom topography, whether it is linear or variable coefficient, etc., etc. So finally, I will show you the convergence of test cases, and No, this is the convergence of the spatial operators and of the trees-based ones, and you can see all of them are second order accurate, except for the Karl operator at the vertices. Now, where does this Karl operator come from? It's the nonlinear terms.
So I think that we have to wrap it up. Maybe you can just go to the next slide and show them the overall ones, and then go to the next one.
Yeah,
and
this is what I was
end
saying.
on the conclusions.
Okay, so this is what I was saying. The in the nonlinear advection term can be split into the gradient of the kinetic energy and the relative vorticity term, which is the curl of the velocity vector. And that because that is fast order, you can see that the convergence plots are first order for the manufactured solution, but it is second order for all the other ones, even though we use 2 second order, 2 third order, and 2 fourth order methods, because this is how we tie it with the the one highlighted in green. This is how we tie it to the first part. And thank you for listening. This is my conclusions, which I've already gone over. And our current and future work consists of extending the analysis to parabolic equation, high order spectral ones in space and time indicators beyond method of lines, which treat space and time together, and design verification exercises in complexity between the barotropic and the full barotropic and the full primitive equations. And these are the relevant publications. And as regards to my current status, as Mark mentioned, I defended my PhD dissertation a couple of weeks back, and I hope to continue working at LANL as a postdoc and collaborate with scientists working on E3SM at LANL and beyond. So thank you very much for listening.
All right, thank you, Sid. And I'll just conclude by saying that this project ended up being this wonderful combination of very practical applications and test cases, and we know that we emphasize verification a great deal, where he's adding term by term and doing all the tests, and then he also extended it to this theoretical part that he's written a manuscript on. So thank you again, Sid.